So, good afternoon and welcome back to this session for Graph Neural Network. Let us continue from where we have left, and I hope I am visible and I am audible and my screen is also visible to you. Uh, Ashwini has sent a big question about its algorithm and page rank. So nothing is out of syllabus. Everything is as per the course handout, as per the bunch of papers which are available to you, and as per the material which is shared with you. We have, matlab, I never uses some in any of the keyword which I have never ever explained in my session. Okay, so I uses the def use pair. So whatever variables which are defined, whatever variables which have been used in the program in the program are defined ahead of it. Okay, so let us quickly move ahead. Acha, this is, I'll have to, I can do it later on. Okay, whenever it will be required, I will be doing it. Now let us start from where we have left. So before moving ahead, I would like to answer any query if you do have. Is there anyone like Avinash? Sorry, Ashwini. Sorry, Avinash. Your name just appeared to me, so I was I was uh, about to call out the name of Ashwini, but unfortunately I called your name. Okay, but before moving ahead, any query to be answered, any doubt to be clarified,
Just
anything,
yeah,
anything to be
just
made?
yes, sir. Can you hear me?
Yeah, I can.
So last time you spoken about this latent variable and latent space, right? So latent variable I got actually, but what about the latent space? So those that latent space is calculated for only the latent variable, or it is for all the variable within the problem, and just to reduce the dimensionality there. So, we generally what we are doing, we are just converting the parameters into the latent space, and again reconstructing the parameter to the actual, space, whatever it is. So I'm just confused. This latent space is only calculated for the latent variable, or is it for all variables?
Okay, now I can justify both yes and no. Suppose let us talk about yes part. So that means space in that case means what all possible values those variable can have is normally called as the space. Okay. So whenever if you're talking about any if you're solving a probability game, then we can say whatever event that that are in your favor or you are taken into account will be called as the favorable event and all. But what all possibilities of all the event will be called as the space. So here also the same thing. If I'm talking about latent space, then because definitely latent space will be defined based on the latent variable. So what all possible values a latent variable can have will be called as the latent space. So directly latent space is related to the latent variable. Okay. Now the other way around also. Latent variable, as per the definition, they're not directly observable or directly countable or directly measurable. So these are the values which have been computed or calculated based on some linear or non-linear combination of the actual variables, attributes or the features. Okay, the feature set of the graph of feature set of those nodes and edges, whatever it be, some linear or non-linear combination of those features, those actual variables, observable variables. So indirectly, if I can say, can I say that the latent space also depends upon those all possible observable variables? Indirectly, yes, because somewhere latent variable are being calculated on those observable variables. So ultimately their range, their possible values, or somehow they are related to those actual observable variable. Okay, so the second is just to justify my statement, but actually latent space is somewhere related to all possible values of latent variable. So to be more precise, the first answer is yes. Latent space is related to the latent variable. But still being a bad person or being a smart, not a bad person, being a person who loves to justify his own statement, then I can also relate it to the observable variables. I hope I have answered your query. Although,
Yes, yes. Actually, just I mean, confused here. So out of suppose 100 variables, there are 50 variables observables which are contributing towards those latent variable, right? So we can only do the dimensionality reduction for only those 50 variables, right?
hmm, but somehow, मतलब indirectly, ठीक है, but let's not confuse you.
Mm-hmm.
Latent space related to latent variable.
Okay.
Because ultimately I cannot work for such a vast feature set. So somehow I'll have to reduce the dimension, and I want to focus on these set of variables, which I call it as latent variable. I hope I have answered your query.
Yeah. Thank you, sir.
This is the beauty of the course. You can justify even matlab, your matlab, partially correct answers also can be justified. I'll not say wrong answers, but partially correct. Okay, so this was the thing that we were discussing last session. I think this week only, because I have taken the webinar session as a regular session because Professor Vipin was not available. So he will be taking some of my session, some of my regular session, and will be delivering the uh, content that was supposed to be delivered in the webinar. Okay, because I should have kept that blank, but if we cancel it, then somewhere else we'll have to place it. And nowadays it is it is becoming difficult to have an extra sessions because the rules have changed for you as well as for us also. So we cannot schedule any of our session anytime, anywhere based on our own convenience. It has to be based, it has to satisfy some norms, some constraint, not the norms, some constraint imposed on us only. By to chodo, imposed on us. Okay, so if you are joining, matlab, if you haven't joined the webinar sessions, so I request to go back, matlab, after this session, go back and listen to the webinar content, because in the webinar content we have covered the topic which prior to this slide. Okay, so ultimately, when I'm talking about the variational autoencoders, it is divided into two parts. One, encoder, which converts the graph, the whole graph, actual graph, into a latent variable, a latent space. Okay, with the matlab, somehow some form of embedding, which in which the whole information can be stored in a smaller dimensions. So this is the activity, and this is a probabilistic activity. Okay, both encoding and decoding is a probabilistic activity, and the decoding part means the decoder of the variational autoencoder VAE, what it takes the that is we can say concised information into account and try to convert, try to reconvert, or we can say try to rebuild the actual graph, which we call it as a cap. So definitely there'll be some loss because my intention will be that I would like to generate the exact graph which was given in the as an input in the beginning itself. But as I have reduced the dimension, some information will be missing. So definitely exactly the same graph cannot be reconstructed. There will be some loss of information. There'll be some distortion in the graph which would be inserted. Okay, now how to calculate what is the loss and all? So in that case, we will be using all sorts of network measures, all sort of similarity measures to find out the difference. Okay, node similarity, edge similarity, graph similarity, all the concept that we have covered in full detail will be used to identify what is the loss, what is the difference between the generated graph, reconstructed graph, and the actual graph. Okay, so what is our main goal? So this is the whole structure of the VAE. Okay, so the main goal is to train our decoder model, which is probabilistic in nature. Definitely both encoder and decoder will be the probabilistic will be the probabilistic functions, okay, or the probabilistic model, stochastic model. They both are the stochastic model. So our main task is to train it p theta a by z. Matlab you have to convert the train the decoder which can reconstruct the adjacency matrix from the latent space or latent variables, from which we can sample the realistic graph. The adjacency matrix A cap, which is an output of the probabilistic activity P theta A by Z by conditioning on the latent variable Z. So in the probabilistic sense, we aim to learn a conditional distribution over the adjacency matrix. This is what we are trying to do. So this A by Z, this bar is nothing that is the conditional dependence, conditional probability, conditional distribution. So we aim to learn the conditional. So ultimately we want to learn the conditional distribution over the adjacency matrix with the distribution being conditioned on some latent variable. So in order to train our VAE, variational autoencoders, we combine the probabilistic decoder with the probabilistic encoder model. Okay, so encoder and decoder both work simultaneously. So this encoder model maps the input graph to a posterior distribution over a latent variable of Z. Okay, so latent posterior distribution. So the idea is that we jointly train both the encoder as well as the decoder. Okay, so both will be trained. My encoder will be trained to convert the concised information into the latent space. Okay, and my decoder is being trained to get that information. After getting that information, his main activity is to reconstruct the actual data. So we jointly train the encoder and decoder so that the decoder is able to reconstruct the training graph when we give them the latent variables, okay, sampled, and which is sampled from the encoder. Then when our model is trained enough, so after training, what we can do, we can discard the encoder. Okay, so his task is done, the trainer's job is done, and generate a new graph by sampling the latent variables from some prior distribution, which is unconditional. So some prior distributions and feeding these samples latent to the decoder. So directly we will discard this part. When you have trained enough, when your participant is trained enough, you can remove the trainer, you can remove his coach, and ask him to perform on any of the summit, okay, sports summit. So this is what the ideal situation which has been assumed, or which for that those decoder and encoder has been trained. So in a more formal and mathematical detail, to build a VAE for a graph, we specify the following key component: probabilistic encoder, decoder, so encoder p phi, decoder p theta, and a prior distribution pz over that latent variable. So we look at each one. You can go through the paper, okay, for more detail. Encoding, or sorry, auto encoding variational base. So the probabilistic encoder model, which is q phi, it takes the graph G as an input. From this input, q phi then defines a distribution q phi z by z over the latent variables. So generally, in the variational autoencoder, the reparameterized trick with the Gaussian random variable, okay, is being used normally, ultimately some form of normal distributions. So is used to design the probabilistic q phi function. That is, we specify the latent conditional distribution z, which is equivalent to n mu phi g and sigma phi g. Okay, that's what I have said. Normal distribution with the mu equals to this and sigma is equals to this. Okay, I've not talked about standard normal distribution, just a normal distribution with certain mean and certain sigma. So where mu phi and sigma phi are the neural networks that generate the mean and the variance for the normal distribution, for which we have taken the embedding. Okay, whereas the decoder model, so the model, which is p theta, what does a decoder do? It takes, so decoder takes the latent representation z as an input and uses this to specify the conditional distribution over the a by z. So conditional distribution over the graph. So here we'll assume that p theta defined a conditional distribution over the entries of the adjacency matrix. That is, we have to compute the probability function, probability distribution function, that p theta at what point in the adjacency matrix. So a uv equals to z based on, sorry, equals to 1 based on z, means we will be checking for each entry of existence of an edge. A uv equals to 1 means there's an edge between u and v. Okay, but this probability that node u and node v has an edge in between, that depends upon the latent variable. Okay, probability that there's an edge between those two nodes is computed based on the latent information, latent space, or we can say latent data of the graph. And the third thing is the prior distribution. So here we adopt the standard Gaussian distribution. Standard Gaussian means standard normal. Okay, prior with the mean equals to 0 and sigma equals to 1. So and which is normally being used in the variational, most of those variational autoencoders. Okay, now comes, so this was the superficial overview. Now let us look and dive deep into the activities. So given these component, These component means the encoder and decoder and the prior distribution. So given these components and a set of training graphs, G1 to Gn. Okay, so we will be having a bunch of training graph as well on which this model will be trained. So we can train the variational autoencoder model by minimizing. So objective function is the minimizing the evidence likelihood lower bound. Normally the function, the short form is called as elbow function. Okay, and this elbow function is a min-max function. Okay, we will be minimizing something and we will be maximizing something. So it is tau summation of all those graphs, training graphs. Gi belongs to Gn. What are they? They are the training graphs. So we'll have to do it for all. Okay, so we'll have to identify the difference, and that difference has to be added for all the graphs. Now, what is the function? So the basic idea is that we speak the maximization, we speak to maximize the reconstruction ability of the decoder. Means this efficiency of this decoder, this is encoder, this is decoder. So the efficiency of decoder has to be maximized so that with the minimum amount of information, okay, at least up to a certain threshold, if that information is complete in that sense, minimum, that this decoder should be able to construct the actual graph. Okay, not actually, or more like more actual graph. नहीं, more actual graph भी कुछ नहीं होगा. More similar graph as it was inputted initially. So that's why. So here we seek to maximize the reconstruction ability. Okay, if I want my reconstruction ability of decoder to be maximized, means this graph should be as close as to G. Okay, so reconstruction ability has to be maximized. That is the likelihood term EQ theta Z by GI for all P theta GI by Z. Okay, based on this information, the graph has to be almost the realistic graph has to be generated. Okay, so this is the maximization activity. We'll have to do it. Whereas, as I've already mentioned, this will be a min-max function. So this we will be maximizing that the reconstruction ability of the decoder has to be maximized. Whereas we will be doing the another activity which will be which have a different objective function. Here the KL divergence. So we will have to minimize the KL divergence between our posterior latent distribution P theta Z by Z and the prior Z, PZ, PZ. Okay, so this have to be minimized. So the key
So
intuition is
just
that.
one question here. This efficiency of the decoder, right? Q theta Z over the Zi, right? How did we come up here, right? I mean, what exactly this function is, and how to calculate this function actually?
This one?
EQ theta, efficiency of this decoder, that one, or over
this
Z
one
over Z. Yeah, this one.
Okay. So this will be the likelihood. You want, how could we, how we come up to this function?
I mean, how to calculate, I mean, what is exactly this function? It's just a term we are using here, right?
As of now, they are just the symbols. We will be looking each one of them in full detail. Not to worry. We'll have a different, that's what I was preparing. The third slide, this one. Okay, so reconstruction loss in various autoencoders. We will be covering that. We will be covering them in full detail.
Okay, okay, thank you.
Not to worry. Okay, what all types? Sometimes the office, MS Office or whatever it be, it works more than expected activity. Okay, not to worry. We'll be covering them. So the key intuition is that we want to generate the distribution over the latent representation so that following two conflict goals are satisfied. The sampled latent representation encoded to the information is allowed to allow a decoder to reconstruct the input. And second is the latent distribution should be as close as possible to the prior information. Okay, the prior. So when we're dealing with these graphs, so the sampled latent representation encode enough information to allow a decoder to reconstruct meaningful graphs from the encoded latent representation when we have the training graph as an input. Now, second is the latent distribution should be as close as to the prior. What is the benefit and how I'll be doing it? So it act as a regularizers in the whole process, and it ensures that we can decode meaningful information, which is the graph in this case. So meaningful graph even when we sample the latent representation from the prior. So even with the prior information PZ, we should be able to generate the meaningful information. So in this case, the second goal, the second one is more important. Okay, so if you want to generate a new graph after training, how can we do that? We can generate a new graph by sampling from the priors and feeding these latent embedding to the decoders. Okay, so this process will work if the second goal is satisfied. If our second goal is satisfied, then we'll be able to do that. Okay, now the question arises, how should we construct the reconstruction loss? Okay, so this is what a question has asked. So we'll be talking about each one of them in a full detail. So this is just a notation how to write the expression. Okay, so the graph reconstruction that involves predicting the original graph or a similar graph from the set of learned representation. Okay, so predicting the original graph, if somehow we have stored the structural information of the graph, we can do that. Okay, or if not exact, then something similar what we want. So, or a similar graph from a set of learned representation need to be generated. So that similar word is again a tricky word. Okay, which means that the graph has to be very much similar to the original. The reconstructed graph has to be very much similar to the original graph. Now, how to find out the similarity? Again, it's not a, because similar in terms of Euclidean space, those numbers will be easy. Mod of E minus EU will give you the difference. And ideally that difference has to be 0. So if those two if those two values are numbers which you want to compare for the similarity, then the similarity means exactness. So you subtract both of those numerical values, the difference will give you how deviate current input is from the original truth. It's easy. Okay, it was very easy when we are dealing with the numerical data, but it is not that easy when I'm dealing with the graphical data. So if I'm given with a big graph and a second graph G prime, if I'll have to find out how similar two graphs are, okay, so I cannot simply subtract both G and G prime and get the answer. G and G prime cannot be a mathematical operation. Obviously, it will be a mathematical operation, but not a direct subtraction. So I cannot simply overlap this graph into the rest. Okay, whatever is being if subtract all the edges, whatever is it is left will be the similarity. No, I cannot do that. So subtraction, multiplication, addition, all the operators that you know that can be done for the Euclidean data or the numerical values cannot be done for the graphical values. Okay. Sorry. So when I simply say similar graphs, it may be easy for me to see, but it's not that easy to compute. So I cannot have a simple operator which just subtract both the graphs, will subtract both the values and give you how similar the two graphs are, or how similar two values are, or how close we are towards the solution. No. So this I think this also include all the 5 to 6 hours that we have invested. Okay, so the similar graphs can be answered. Was answered if can be answered if you have an idea of all those 5 to 6 hours content that we have covered in the beginning itself. Okay, so that's why I was emphasizing more. Now I need not to find out. I need not to explain you how to find out the similarity. Okay, so the reconstruction loss measures the difference between the predicted graph and the original graph. So difference in a graph, it's not just subtracting one value to the another one. So it's not direct, it's not a direct activity. The goal is to train, the goal is to train the GNN, graph neural network, such that the reconstruction loss is minimized. That is, to encourage the generated graph to be similar to the input graph. I know if I'm using if I'm explaining in English, it's easy. I have to generate a graph which looks like similar to the original graph. But how to ensure that it is similar and how to measure that is similar, that's not a direct activity. Okay, that requires at least big O of n square. You'll have to go through each and every nodes or each and every part of a graph. So that reconstruction can either be node level reconstruction or the graph level reconstruction. We'll like a look at each one of them separately. So when we talk about node level reconstruction in the reconstruction loss, so for the node level reconstruction, the GNN aims to reconstruct the attributes or the embeddings of each node in a graph. Okay. And in the previous session, you have an idea how to find how to identify the embedding of each node of a graph. Okay, so that node level reconstruction, we will have to find out that the difference has to be less. So the reconstruction loss can be defined using a suitable distance matrix. Okay, so either we can use it as a mean square error or a binary cross entropy between the predicted and the true node representation. Okay, when we talk about graph level reconstruction, so in the graph level reconstruction, our goal is to reconstruct the entire graph structure. So the reconstruction loss can be formulated based on the graph adjacency matrix, edge prediction, or any of the other graph representation. So commonly used graph function, which include for this graph level reconstruction, will be the binary cross entropy loss, for the edge prediction or the graph similarity matrix. How similar those two graphs are. Okay, so let us look at each one of them in a bit detail. So one of them was binary cross entropy. Just give me a minute. Okay. So binary cross entropy, the formula is minus 1 by n sum of all the log values of pi. So binary cross entropy BSE is commonly used for the loss function in the machine learning, particularly in the whenever you have a binary classification, whether 0 or 1. Okay. How many zeros are there who are supposed to be 1? How many ones are there who are supposed to be zeros? So it measures the difference between the predicted probability distribution and the true distribution for a binary outcome. So binary cross entropy compares each of the predicted probability to the actual class output, which can either be 0 or it can be 1. So it then calculates the score that penalizes the probability based on the distance from the expected value. So that means how close or how far you are from the actual value. Okay, how close you are or how far you are. Okay, it is a negative average of the log of the corrected predicted probabilities. Now, the reason why we are taking those log values, so reason behind using the log value is the log value offers less penalties for the smaller differences between the predicted values and the corrected values. Okay, so small differences need to be penalized less, and small and the bigger difference need to be penalized more. So this can easily be done by using the loss function. Okay, so that's why the log values, those log values are used. So log values offers less penalties for the smaller differences between the predicted probability and the corrected probability between the ground truth. When the difference is large, the penalty will have to be large also. So for lesser, it should be lesser. For larger, it should be higher. Okay, so this is the reason why we use the log function, because we have to emphasize more on the bigger differences. So we calculate those log values for all the corrected probabilities, since all the corrected probabilities lies between 0 to 1. So all log values are, because they all lies between 0 to 1. So that's why all of them, all the log values will be negative. Okay. So if all the values are negative and somehow I'll have to make it positive. So that's why the negative sign is being imposed, or it is being put in the beginning of the formula. Because all the log values will be negative. So how to make it negative? How to make those negative values in a positive way? By assigning them, by multiplying the whole model by -1. Okay, so in order to compensate for these negative values, we use the negative averages for all the values to make it positive. Okay. So in the context of graph generation, we have adjacency matrix. So BCE, binary cross entropy, is often used when dealing with the binary graph, either the presence or an absence of an edge between those two nodes. Okay, so here A is the predicted adjacency matrix. Okay, whatever your predicted adjacency matrix is, and Y is the true adjacency matrix, means the ground truth. Okay, so the predicted matrix and the real, or we can say the correct adjacency matrix. Okay, Now, so for each single entry in that matrix, so suppose if this is A and this is Y, okay? So for a single entry in a matrix, let Aij represent the predicted probability of an edge between I and node J, and Yij represents the true level. क्या explain कर रहा था मैं कुछ भूल गया. I was explaining about A and Y only, sorry. Okay, so A is the predicted adjacency matrix that have been recently been generated, and Y is the actual transgency matrix. Okay, so this is the outcome of the decoder. So for each single entry, means this one, for each single entry, let Aij represent the predicted probability of an edge between the node I and node J. So if at this point 2, 3, this the single entry of this matrix to A23, okay, what does it represent? It represents the predicted probability of an edge between node 2 and node 3 of the graph. The predicted probability of an edge between node I and node J, and Yij represents the true level. Okay, so Yij represents all the true level, means the actual ground truth. So 1 if there's an edge, or 0 if there is no edge. So means the structural information from the graph. Okay, so BCE, binary cross entropy loss, for a single entry will be calculated in this way. Okay, so BCE, there's some pre-processing work which has already been done in my previous session, and unfortunately I had not deleted the previous sessions entries, but okay, I can use the same. So as I say, this is a binary. So binary cross entropy loss for a single entry for each and every entry. So Aij, Yij. Okay. Now to make it easy, let us consider it to be a number. So suppose I equals to 5 and j equals to 7. Okay. So that means if this is the I and this is the j. Okay. So A57, suppose this is 5 and this is 7. This entry I'm talking about. Okay. So binary cross entropy of the A and Y's is equals to, this is given based on the formula, Yij into log Aij. Okay. Plus 1 minus Yij into log 1 minus Yij. Now suppose Yij is equals to 1. Okay, so in that case, one time it will be 1, the other time it will be 0. So if I say that Yij is equals to 1, then definitely 1 minus Yij will be equals to what? 0. If this is 0, 1 this time, it will be 1 this time. Okay, so either of them, either Yij or 1 minus Yij, one of them will be 0 at a time, and the second part should be, so one of them is 0 at a time, then in that case another one will be 1. So if Yij is 0, if it is 0, then 1 minus Yij will be 1. Okay, into log of aij, and in the second part log of 1 minus aij. Okay, so either if ij equals to 1, then yij will be equals to 1 and log aij will be a different value. It will be non-negative. So that means 1 minus yij, 1 minus 1 and log of 1 minus 1. So this will be 0 into log 0. Okay, so this is how the binary cross entropy is calculated. Although the formula may look difficult, but one term will be 0 at one time and another term will be if it is 0 for this time, 1 next time. If it is 0, if it is 1 next time, then 0 next time. Okay, so either of them will be 1, the other part will be equals to 0. So when the observations belongs to the class 1, the first part of the formula become active and the second part will become 0. So the second part vanishes, but in the vice versa means if this part is equals to 1, so 1 minus 1 0 and so on. So it will be either based on this first part or it will be based on the second part. So one of them will be 0 and the other one will be non-zero at the same time. So when the observation belongs to the class 1, the first part of the formula become active and the second part vanishes because it becomes 0 now. And vice versa. Vice versa means if somehow the second part becomes 1, then the first part will be equals to 0. Or if the second part is equals to 0, then the first part will be equals to 1. So vice versa in the case observation actually class belongs to. So this is how we calculate the binary clause. Okay. So the expression penalizes the model more if it is predicting a high probability for a non-existing edge. Okay, so if suppose there is no edge between two certain nodes of a graph. Okay, and if my model predicts that edge, then that means this is an error. So my model should be able to punish those kind of decision also. So this expression penalizes the model more if it predicts a high probability for a non-existing edge. Okay, so high probability of non-existing edge means it is saying that okay, chances of being edge over here is more, but actually there is no edge in the actual graph. Okay, so penalized, the penalty have to be high. Same is the case. There's one more scenario where the penalty has to be high or a low probability for an existing edge. When there is an actually there is an edge between those two nodes of a graph. Actually there is, but mod does not predict it, or it predict it with certain low probability. Okay, clear? So the overall BCE, binary cross entropy loss for the entire adjacency matrix can be computed by averaging the loss of all the entries for I equals to 1 to n, j equals to 1 to n, 1 by n. Okay, summation of all those BCE for aij and yij. So this will be the binary cross entropy loss function. So in practice, many deep learning frameworks such as TensorFlow, PyTorch, they all provide the built-in function to compute the binary loss functions. So making it easy to incorporate into the model training process. We can directly implement it. Okay, and this can only be computed based on based on the existence of an edge at each pair of node. Okay, so you'll have to do it for each pair of node.
So here
The question.
AIJ Yeah. So for Aij and Yij, both are matrix, right? So both can have a 0 or 1 value, is it?
G.
Not not between 0 or 1. It's can it should be 0 or 1.
Huh. Okay. Mm, huh.
I mean,
It
it's a
can be
binary
0.
problem, right? It's a binary
If
problem.
it is a binary problem,
Yeah, either there's a age or not, right?
huh.
So
If there's
suppose
an
for mhm.
G,
Suppose
bolo.
for Y11, we are comparing for Y11 and A11, right? Both are either matching or not matching, right? Either both will have 1 1 or 0 1, right? So there are two possibilities. Either they are matching or not matching, right? If they are matching, then BC will be 0, loss will be 0, right? There's no loss. If they are not matching, there will be a loss.
Huh. So this
But
is
how?
one way. G.
Mhm.
Sorry.
Sorry.
नहीं आप फिनिश कीजिए.
Yeah. So how to calculate that loss here by value actually?
Okay. So that's why this was for each node.
Or each edge or node. Okay.
हाँ मतलब pair of nodes. For each pair
Okay.
of nodes.
Mhm.
Either there will be an edge or there will not be an edge. Okay. Actually मैं मतलब where there should be an edge, and if it is yes or no. So it will be yes or no, and based on that zeros and one, it will be calculated. If we'll have to do it for whole graph, then it will be a summation of all those i's and j's from 1 to n. So we'll have to do it for all the pairs for each and every position. And definitely at the end, we'll have to normalize it by 1 by n.
Yeah. Just confused actually. So if I have Aij equal to 1, right? Or right, if I take Aij equal to 1 and Yij equal to 1, suppose we'll take 1 1 here. Okay, then first term, yeah, first term will be activated, right?
Huh.
Uh,
Okay.
yeah.
There are two matrices.
Mhm.
One is the adjacency matrix, means this is the outcome of the decoder.
Yeah, I mean, we are just checking the loss between both the matrices, right? Both the adjacent matrices only, right? One is predicted, one is true matrix,
Hmm.
and
True
we are
means
calculating.
the actual graph.
Yeah.
Okay.
Mm-hmm.
So this is the adjacency matrix of the actual graph. And this is the matrix of the predicted graph, the outcome of the decoder. So what can be the possibility? Let me call it as A and let me call it as Y. Okay. Now, there are multiple scenarios. There was an edge in the actual graph. Okay. There was an edge between actual graph. So suppose this is node number 5 and node number 7. Okay. So there is an edge. There is no edge between 5 and 7. And so is the case, the predicted graph as well. Okay. There is no edge in the original graph, as well as the predicted graph also does not have any edge. Okay. Second possibility can be for some different pair, for suppose 3 and 2, there was an edge. And same is the case, there is an edge in the predicted graph. So in this cases, in both the cases, there should not be, matlab, there should be a 0 and there is a 0. Second is there should be 1. There is a 1 in the actual graph and there is 1 in the predicted graph. So that means edge होना चाहिए था, edge है. Edge नहीं होना चाहिए था, edge नहीं है. Okay. This is not an error. This is the correct. This is the correct output, a correct prediction. Error will be when it should not have a edge for some different pair of node, but there is. Clear? The other scenario can be that there should be an edge in the actual graph, but in the predicted graph, the edge is missing. So these are the error conditions. Okay. So for a single matrix,
two possibilities. Yeah, go ahead, please.
If the output is, मतलब if the prediction is correct, 1 होना चाहिए था 1 है, 0 होना चाहिए था 0 है. But the error will be 0 होना चाहिए था वहां 1 है, and the second error can be कि 1 होना चाहिए था वहां पर 0 है. So for a single entry in the matrix, Aij represent the predicted probability of an edge between a node, and J represent the true where 1 if there is an edge and 0 if the edge is missing. Now, if I'm doing it for every single entry, Aij, and I'm comparing Aij and Yij. Okay, so BCE, binary cross entropy, for each index of a node. So minus Yij into log Aij. Okay, so suppose it was supposed to be 0 and there is a 0. Okay, so in this case 0 into log 0 कितना होता है? How what is the value of log 0?
Undefined.
Okay, so 0 into something 0. 1 minus, so it was 0, 1 minus 0, it will be 1. And log 1 minus 0, log 1.
Log 1 is 0. Base 2, I mean, yeah.
Clear? So this will be 0. So actually there was no, and this gives me 0. The other way around. So in either case, 1 will be, so Yij and 1 minus Yij. It is, if it is 1 this time, it will be 0 here. If it is 0 this time, it will be 1 here. Same as the case Aij also. If Aij is equals to 1, this value, if it is 1, this should be 0 in the second. If it is 0 in this expression, it will be 1 in this expression. Okay, so if it is 1, then it will be 0. If it is 0, it will be 1 over here. If it is 0 over here, then it will be 1. If it is 1 over here, then it will be 0. So I'm taking, but actually one of the expression will be 0 and the other expression will be non-zero. So when the observation belongs to the class 1, the first part of the formula become active. Okay, and the second part vanishes. It will be 0. But and the vice versa, means the first part vanishes, then the second part will become active. In the case observe, so vice versa in the case observations, actual class are 0. So this is how you will calculate the binary cross entropy. Clear? Is it good? So this is how a binary case can be dealt. In the statistics, had you gone through that statistics course? It was in the under the towards the end of the course, there was exponential smoothing, if you do remember. Okay, exponential smoothing, and in that exponential smoothing, there were two formulas: Holt double exponential and Holt Winter triple exponential. There you uses alpha, beta, gamma multiple parameters. So in that case, you were multiplying alpha and 1 minus alpha. So if alpha, in that case, if it is not a binary one, then if it is 20%, 80% over here. But in this case, sorry, I have taken a wrong example. Forget that example, because it accepts the real values between 0 to 1. But in this BCE, binary cross entropy, it accepts only the zeros or ones. If it is 0, if first part is 0, the other part will be non-zero. If the second part is 0, then the first part will non-zero. So either in either case, one of them will give me a non-zero value, and the second part will give me a zero value. So one of them will be active. So this is how it will be, whether there is a mismatch or not. Zero tha, zero hai, no mismatch. One tha, one hai, no mismatch. Zero tha, one hai, there is a mismatch. One tha, zero hai, there is a mismatch. Okay, so it will clearly come up whether there is a mismatch or not. So this expression penalizes the model more if it predicts a high probability for a non-existing edge or a low probability for a existing edge. Means the penalty function should be more if you predict that there should be an edge. Okay, you predict that there should be an edge between those two nodes, but actually in the actual graph, the graph doesn't the edge doesn't exist. Okay, so high probability for a non-existing edge. Actual man, there is no edge in the actual graph, but the model predicts that there is an edge. Okay, that's again a penalizing function. Means 0 ko 1 kiya. Same, the error is also for a low probability for an existing edge. Means there was an edge in the actual graph, but it predicts that there is no edge. Means low probability for an existing edge, means 1 ko 0 karna. When actually there is a 1, the model is predicting me 0. When actually there is a 0, model is predicting 1. In both the cases, the penalty has to be more. Okay, and the model should be able to penalize it also. Okay, you're giving a wrong prediction. So this was for each value, these for each pair of nodes. So we'll be doing it for all the nodes of a graph. So overall, BCE loss for the entire adjacency matrix will be summation from I equals to 1 to n, summation from j equals to 1 to n, normalized by 1 by n. Clear?
Yes, sir. Yes, sir. So just one, I mean, we can also use the XOR functionality here, right? Anyway, if the nodes are not same, it will give us 1. If it is same, it will give us 0, right? So either we need to get it 1 or 0, right? There's error, then it will give us 1. Otherwise, it will give us 0, right? So we can apply the XOR functionality also here, between Aij and Yij,
For
values.
matching, for identifying the matching and a mismatch, we can. For 0, initially it was 0 and it is 0, fine, match. Initially it was 1, now it is 1, that's match. So matching, yes. Mismatching, penalty or no. We can.
Okay.
And this is, actually this can be done in that way also, na? But XOR function, what is the actual implementation of an XOR function? Uh, uh,
If the values are same, it will be 0. If it is
हाँ
different, it will be 1.
हाँ fine.
Hello, sir.
नहीं yeah, let me
Uh,
check. जी बोलिए.
Actually, I want to add one point.
हम्म.
Bhupendra, you are missing one thing. Like AIJ at initial stage of training, it should not like return 0 or 1.
So you
Okay.
mean while calculating the error, right?
Yes, that's why you are calculating the error, and it should like okay, what can I say?
Input differs.
Ideally, it should be 1 or 0, but if we start training at earlier stage, it should differ from like 1 or 0. That's what we are penalizing here, like with that loss function. So
The input will always be 1 or 0. We are training because of getting the parameters, not the
but
values.
yeah,
नहीं,
but
So 1 0, yeah, 1 0 will not change. So it will be 1 and 0. We are doing training only for getting the parameter values, the weight parameters, not the values of the A or Y. It is
okay.
always be 1 and 0. We do the back propagation only to get the
Yes, but we
weights.
don't know. Okay, you can go ahead.
So ultimately, our goal is to check whether actually there was an edge or not, or my model has predicted wrongly. So that's all. I don't think there's any confusion in it. How you are actually doing it, that's a different point. But ultimately, we are checking the मतलब in sense whether it is zero or मतलब initially it was zero, now it is zero. Initially it was one, now it is one. So that's a success. And if there's a mismatch, zero or one or zero, then it will be a penalty. Either I'm not able to understand your question, or
Yeah, I mean that's okay. I mean we can so as I XOR function is like if there are two values, right, x and y, so we can say x plus y minus 2xy. By using that function also we can calculate the error. That's what I'm saying actually.
नहीं ठीक है, but that मतलब but we have not been using the digital logic anywhere in terms of zeros and ones, because we are converting it in the form of a mathematical functions. So either you can use the XOR functionality, but XOR gates and all, it will be in terms of electronics, na, digital gates and all. But here we'll be dealing in the form of a matrices. The values will be zeros and ones. So your digital logic works well when you're dealing with the signal processings and all. It will be easy for you to compute. But here it will be a mathematical operations. Although functionality remains the same, how we are doing it, it is the same logic. But here, the electrical signals or something, these are the values of a matrices at each index.
Yeah, I mean got it actually.
हाँ,
Thank you.
concept ठीक है, लेकिन but I cannot use those digital gates as operators in this case, because these are not the signals, these are the values of the matrices. If I can convert, but why should I do that? Just to make my one task easier, I'm adding new things. मतलब why I should use the digit? मतलब ठीक है, either I'm not able to understand your question or I'm
No,
not
no,
able to
I'm not saying
satisfy
the
you.
digital one. We can use the
Ah,
XOR function actually. So that is x plus y minus 2xy. So it will give the
I
same
think
one.
No, XOR
XOR
function will
function
not be
XOR function cannot be used because it won't be
applicable here.
differentiable, because in neural network we need differentiation to back
Yes,
propagate.
XOR
We
Right.
function
cannot
is
use
not
that.
applicable in neural network. XOR
okay,
function
let
is
me
not
check.
applicable in neural network. It is a iteration will go on, right? And from there we have to find out the weights or the parameters.
Okay, let me check. Is it
Okay.
differentiable? Is XOR function differentiable? Oh, pure logical XOR is not differentiable. So I think whoever who would answer, I have not even thought of this. Okay, thanks for clicking this point. Who had suggested that that function is not differentiable? Can you please raise your hand? I need your. Matlab, can you please help me? Who had suggested a function to be different, not differentiable? Am I audible? Suddenly the. Am I audible? Yes or no?
Yes, sir. You're right.
Yes, sir.
अच्छा ठीक है. So thanks for the answer. Well, I was not that point didn't click into my mind. The XOR function is not differentiable. Although the functionality is same, but it's not differentiable. Chalo. So, but I would like to thank that person who had helped me to answer this question. That's what that's why I was asking for who had helped me. Chalo, no issue. If you want to be hidden warrior. Okay. The second is the I have heard. As far as I can think, I have covered this similarity one. Is it so? This function,
Yes, sir.
please confirm.
Before midsem we
Before
covered.
midsem, I have covered. Na? So that's what this expression. I have covered this graph similarity. So that's why let me check. Graph similarity I have covered. So again, the similarity will be in that sense. So I should not again cover the same topic, and I can quickly move forward. Was it C? In lecture 7, let me check. हाँ, ग्राफ सिमिलैरिटी वही तो मुझे याद आ रहा था कि मैं कवर कर चुका हूँ fully. हाँ फिर ठीक है. So that's easy for me. Now I need not to cover that slide. Okay, so I can quickly move back. So these are the similarity values. The only thing which was not covered was the graph reconstruction loss in graph based. Okay, so one of the reconstruction loss method was the binary cross entropy, and the another reconstruction loss mechanism was the graph similarity. Okay, this we have covered. Now let's move forward. So for the variational autoencoders for the graph data. So now we'll cover two different ways in which graph variational autoencoder idea can be initiated for the graph. So either approaches differ in how to how they define the encoder, decoder, and the latent representation. So one is the node level latent, and the another is the graph level latent. Okay, so you can go through this paper, Keff and Willing, Variational Graph Autoencoders. It was published in 2016. So the idea was first proposed by them, and the term was VGAE. Okay, Variational Graph Autoencoder. This E have been taken from it, and autoencoder. Okay, so this framework is for the unsupervised learning, and this model make use of latent variable and is capable of learning interpretable latent representation for the undirected graph. How does they do? So the key idea in this approach is that encoder generates the latent representation for each node in the graph, and the decoder takes the pair of embeddings, okay, as an input, and use these embeddings to predict whether there should be an edge or not. So predict the likelihood of an edge occurring between those two functions. Okay, so likelihood estimation, like a thing. Okay, we are trying to generate whether there should be an edge or not. Okay, again the probability, but that's again a probabilistic function. So the definition is, so they work on an undirected graph, undirected unweighted graph with number of vertex set as V and edge set as E. Okay, and N is the mod of V, means number of nodes. So N contains the number of nodes in the graph. Adjacency matrix A of G is introduced assuming the diagonal element is set to be 1. Okay, so all the diagonal elements are set to 1. That is, every node is connected to itself. And its degree matrix, which is D. So they further introduce the stochastic latent variable Zi, summarized in a matrix of order n cross f. Node features are summarized into the matrix of S of the order n cross D. Okay. And this model uses the GCN, graph convolution network, encoder and simple inner product as a decoder. Okay. So how does the encoder model works? So this model uses the GCN. In particularly, you are given within adjacency matrix a node. So an adjacency matrix, a node features both, and they uses two separate GNN, two separate graph neural network to generate mean and variance parameter for each one of them, respectively, condition as is posed. So mu z, mu z will be mean of that distribution, GNN mu of a by x, sorry, not by ax, okay, and the variance, the log function of the variance. So log standard deviation of z, 6 sigma z will be based on x and z. So mu z is a mod V cross D dimensional matrix. It specifies the mean embedding for each node, and log z will be of the will be of a set of real numbers of the order V cross D matrix. Similarly specifies the log variance for a latent embedding. So encoder, so latent node embedding will be computed in this way. Z equals to epsilon, okay, sum product of exponential function of the log function plus mu z. So here epsilon will be a normal distribution between 0 to 1. Is a V cross D dimensional matrix with independently sampled unit normal entries, given encoder parameter as mu z and log sigma z. Okay, mean and the log variance. Whereas the decoder model, this was the main function. So decoder model means it is simply the inner product. So simple inner product is used as a decoder. P theta a by u equals to 1 based on zu and zv. It will be the dot product of zu dot zu transpose zv. Okay. To construct the reconstruction, to compute the reconstruction loss, what they assume? They assume the independence between the edges and define the posterior p theta g by z over a full graph in this form. Okay, so product of, this is the product. So product of all UVs, all the pair of edges. Okay, UV that belongs to V square means second order. So all a pair of edges such that there's an edge between those two nodes. So AUV probability of AVA UV equals to 1 based on their latent information. Okay, ZU and ZV. So which corresponds to the binary cross entropy loss over the edge probability. So to generate a discrete graph after training, what we can do, we can simply, we can sample the edge based on the posterior Bernoulli distribution, zeros and ones. So latent space of unsupervised VGA that was model trained for a Cora citation network. Okay, this is what their output is. So here the gray lines, these that denotes the citation links, and the color green, purple, red, orange, and all yellow. So the color denotes the document class. Okay, which was not provided during the training. So that's why it was called as unsupervised learning. And they end up with the research papers of various domains. Okay, there was one more graph VAE in towards generation of a small graphs using variational autoencoders. Okay, Simorsky in the year 2018, they give us an alternate node level VAE approach. So researchers have also defined variational autoencoder based on graph level latent representation. So in that approach, what they have used, so they uses the same elbow functions to train the VAE model. However, the encoder and decoder function was modified to work with the graph latent representation in the form of GZ. So graph level variational autoencoders was the first approach by the Simonsky and Komodakis in the year 2018, and they named their algorithm as graph VAE, graph variational autoencoder. Okay, the full form remains the same, but somehow they have made some differences. Just give me a minute. So they renamed the algorithm, okay, as graph VAE. Okay, it was just a name given by them. So they coined graph VAE in a chemoinformatics activity. So on the task of molecular generation. So molecular data set are the challenging but convenient test bed for the generative models, and they easily allow both qualitative and qualitative tests for the code. So graph VAE method is applicable for generating small graphs only, and its performance leaves space for the improvement which can be improved further. So as a graph VAE output, a probabilistic graph that do not assume having a prescribed order of reconstruct transformations available, they formulate the learning problem as a autoencoder. Okay, so this was the structure of their work. So they graph. So they have the adjacency matrix of order n cross n, E set of edge set. So the discrete attributed graph G, which contains A, E, and F of n nodes. A is the adjacency matrix. Okay, and the chemical data that they represent was the polypropylene oxides. Okay, so A is the adjacency matrix. E is the edge entry and attribute tensors, and F is the node attribute matrix. Okay, so this was their input. This was the graph. Based on that graph, they converted all the three, not converted. They computed the adjacency matrix, edge tensors, and the attribute matrix of the node attribute matrix. Then they have the stochastic graph encoder G phi, sorry, Q phi Z based on the graph. Okay, so there comes the encodings. So this stochastic graph encoder embeds the graph into a continuous representation of latent space. Okay, given a point in the latent space, the novel graph decoder, so this and the Y itself, was given to was converted into the latent space PZ and Y. So given a given a point in the latent space, the novel graph decoder, which is this P theta G, based on the latent information, generating a graph based on the latent information, outputs a probabilistic fully connected graph. Okay, fully connected graph, whatever it be. So G, E, and F on a predefined K, which is greater than or equals to N nodes, for which the discrete sample may be drawn. Okay, theta and phi are the learnable parameters. Pz is a regularization, and the process can be conditioned on a label Y for controlling the sampling of a test time, so that the reconstruction ability of the encoder is facilitated by approximate graph matching for align G and G prime. Okay, so the graph matching algorithm for G and G prime can be used. So here in this case, the first term L is the reconstruction loss that enforces high similarity for the sample generation graph for our input G. Okay, the second term is the KL divergence that regularize the code space to allow the sampling of Z directly from the PZ. Okay, instead of Q phi Z by G, directly from the regularization function PZ. So they can be directly used from Z. Dimensionality for Z is usually small because it only works because in the beginning itself they have mentioned it works for smaller graphs only. Okay, this method is not capable of dealing with the larger graphs. So that dimensionality of Z is usually fairly small, so that the autoencoder is encouraged to learn a high level compression of an input instead of learning a simply copying and giving the output. So while the regularization is independent of the input space, the reconstruction loss must be specifically designed for each input modality. Now, what is the difference? So the critical difference between the graph level encoder and the node level encoder from the previous section is, here we are generating the mean mu zz that belongs to the set of real numbers of dimension d, and the variance log sigma z of the graph. Okay, for a single graph level embedding. Whereas in the previous section, wherever we were dealing with the node embedding, we defined the posterior distribution for each individual node. And here we are doing it for the whole graph. So this is the difference. This is the only difference between the graph level embedding, graph level latent, and the node level latent. So as a summary, learning to generate a graph is a difficult problem for a method based on the gradient optimization, as a graph are discrete structures. So issue was resolved by having a decoder output in the form of probability graph distribution for a predefined size directly at once. Okay. On the other hand, learning the order of incremental construction involved discrete structure which are not differentiable. So this was resolved by the reparameterized trick. Okay. In a probabilistic graph, the existence of a node and edges as well as their attributes are modeled as an independent random variable. The method is formulated in the framework of variational autoencoders. So VAE are a popular framework for a deep generative model, not just for the graph, but for the images, text, and wide variety of data domains as well. Variational autoencoders have well-defined probabilistic motivation, and there are many work that leveraged and analyzed the structure of a latent space learned by those VAE models. So not only for the graph, it can also be used for many other, but they have some limitation. So have a VAE also known to suffer from severe limitation, which is image processing domain, specifically in that the tendency of VAE to produce blurry output in the image domain. So that if we are using it for the image domain, they will generate the blurry output. Many recent state-of-art generative model leverage the alternate generative framework with GANs being one of the most popular that can be used for get rid of this scenario. Okay, so this was related to variational autoencoders. Now, next is GAN, generative adversarial network. Okay, the second method of generating the deep generative model. Someone was trying to unmute himself. Any query to be answered? Okay, thank you, Bhupendra. Any query? Someone was, I was able to hear some sound. Should I continue? I'll have to finish it. Now the second is GANs, generative adversarial network. Okay, so these are the class of neural network that are trained to generate a new data that is similar to the training data set. So here it is of two part. One is the generator network, which generates the new data samples, and the another part is the discriminator. So that part is to identify whether it is being generated by the generator or not. So that tries to distinguish between the generated samples and the real samples. Okay. So the main activity of the discriminator, generator network is to generate the structure which is more realistic. Whereas the activity of the discriminator is that to identify even with a small loophole or with a small drawback or a mistake, he has to be able to identify whether that is generated by the generator or it is a real-time data. So GAN has been successfully in generating the realistic images, videos, and audios that have been applied to the variety of applications, including the art generation, data augmentation, and synthetic data generation. Okay, you can go through those blocks to understand more. So GAN are used for generating new data that are similar to the training data set. So it can be used for the variety of machine learning tasks such as image generation. So GAN can be used for generating new images that are similar to the training data set for applications such as art generation, data augmentation, synthetic data generation. For video generation, GANs can be used to generate new videos that are similar to the training data set for applications such as video prediction and video synthesis. Third is the text generation. So they can also use to generate a new text that are similar to the training data set. Okay, so language translation or text summarization. Okay, still that is not perfect, but still we are using it. Fourth, data augmentation. So to generate the synthetic data that can be used for the data augmentation, improving the performance and accuracy of the machine learning process. Art generation. So generate art and other creative work demonstrating the potential of AI for artistic expression. So for that, GNs can be used. Synthesis of the data. The GNs can also be used to synthesize a new data that is similar to the training data set, expanding the available data for machine learning and AI applications. So there was a bunch of researchers, Kiff and Cow. They come up with a new keyword, Moigen. Okay. And the name of the paper, the title of the whole paper was Moigen, an implicit generative model for a smaller molecular graph. So that means for the biological data only. So first, matlab V means they. So they define the trainable generator network G theta. RD tends to X. This generates the network. So this generator network is trained to generate the realistic but artificial data. Realistic but fake data samples by taking a random seed, latent space, a latent variable, random seed as an input, sample from the normal distribution. And at the same time, there's a discriminator network, which gives me a value between 0 to 1. And the goal of this is to distinguish between the real data sample and the sample generated by the generator. So either this is generated by the generator or this is a real data sample. Okay. So here we'll assume that discriminator output the probability. Obviously, that will be a probabilistic function that gives the that a given input is fake or a real. Okay, the probability by which it is a fake. Okay, so here also the main function is something like this. So to train again, both generator and discriminator are optimized jointly. Okay, both of them are optimized as a min max function. So min of theta and max of phi. Okay, Ex that belongs to the data, log 1 minus d theta x plus Ez, that is from the p seed z, means getting the input and generating the log d theta, sorry, d phi g theta z. So here p data denotes the empirical distribution of a real data sample, that is uniform sample over the training set, and p seed denotes the random seed distribution, a standard multivariant normal distribution. Okay, multivariant, where there are multiple variables. So this equation above means this one is a min-max optimization. So the generator attempts to minimize the discriminative power of the discriminator. Means whoever is generating those samples, that data, it tends to minimize the discriminative power. Means that the discriminator is not able to identify, is not able to distinguish between the real and the artificial. Okay, so generator, the objective of the generator is, the generator is attempting to minimize the discriminative power of the discriminator. Means minimize the discriminative power means he is not able to judge it more, shrink the difference. Okay, while the discriminator, the second part of the model, the discriminator is attempting to maximize his ability to detect a fake sample. Okay, so he want to be perfect in detecting the fake samples. So even with a small difference, the discriminator should be able to identify that this is a real data or a fake data. So that's why it is a max min function. Okay, so maximization of phi, maximizing the ability to detect the fake sample, and the generator, its objective is to minimize the discriminative power of the discriminator. Okay, so he want to ensure that he is not able to distinguish it, but the discriminator want to ensure that even with a small difference, I'll be able to distinguish whether this is a real or fake. So that's why it is min-max approach. Same like encoder and decoder also. So one important benefit of GN based framework is that it removes the complications of specifying a node ordering in a loss computations. Okay, so that means so as long as the discriminator model is permutation invariant, which in case of almost every GNN, then GNN approach does not require any node ordering to be specified. Okay, so if this is the case, then ordering of the adjacency matrix generated by the generator is immaterial if the discriminator is permutation invariant, even with a small change. You can give them in any orientation, he does not require it. But the only difficulty involved in GNN is in the min-max optimization. How well we can ensure that this are being achieved. So they introduced Boygen molecular, what is the full form? I'm missing Boygen molecular integrated. No, this I stand for something else. I have not mentioned it. Is this? Oh, sorry. This is not I. Meri galti. This is not I. This is MOL. Molgen. I pronounce it wrongly. That's Molgen. This is not I. This is small l. This is not capital I, small l. So molecular. Okay, molecular gain. Okay. So they introduce Molgen, an implicit likelihood-free generative model for a small molecular graph for the biological. Okay, biological data only. That circumvent the need for expressive graph matching procedure and node ordering heuristics of the previous likelihood-based method. So this method adopts the GAN generative adversarial network to operate directly on the graph structural data. They combine their approach with the reinforcement learning objective and encourage the generation of a molecule with a specified designed chemical properties. So they predict the generative model of Molgen predicts discrete graph structures at a once. Predict the graph completely at a once, and that too non-sequentially. For computational efficiency, although sequential variant are possible in general. So Molgen further utilize the permutation invariant discriminator and a reward network, okay, for the reinforcement learning based optimization based on GCN, graph convolution layers. So this is their structure. From the latent, or we can say priors, they generate. So these are the generators. Okay, this is the reward network, zeros and one. This is the discriminator, whether that is real or fake. Okay, so a molecular graph is given, and this is reinforcement learning. Means if you give a correct decision, you will be awarded. If you give a wrong decision, you will be penalized. So what is the schema for this? So schema for Molgen is a vector Z is sampled from the priors and passed to the generator, which the output representation of a molecule. Then the discriminator classifies whether the molecular graphs come from the generator or from the data set. Okay. And there's a reward network that tries to estimate the reward for the chemical properties for a particular molecule provided by the external software, whether it has made a wrong decision or whether it has made the correct decision. So this is the architecture. So this figure outlines the Mulligan. From left, the generator takes the sample from the prior distribution and generate a dense adjacency tensor. Okay, A and an annotation matrix X. Subsequently, the sparse and discrete A tilde and X tilde are obtained from A and X respectively by the categorical sampling. Okay, so not the complete, some sampled set are being computed. Now the combination of A and X, A tilde and X tilde are represented, sorry, A tilde and X tilde represents an annotated molecular graph which correspond to a specific chemical compound. And finally, the graph is processed both by the discriminator and the reward network. Okay, discriminator and the reward network that are invariant of the node order permutation based on relational GCN layers. So this is an implicit generative model for the molecular graph for the smaller size. Through the joint training of GNN and reinforcement learning objective, the model is capable of generating molecular graph with both higher validity and novelty than the previous comparable VAE models, VAE based generative models, while not requiring the permutation dependent likelihood function. That's okay. Then the third is the autoregressive method, okay, which generates the graph in an iterative, we can say iterative manner, and in a what to say, it's like the another version of the preferential attachment, preferential attachment. What we call it, iteratively grow. Okay, do I have a time? Hardly 10 minutes. Will I be able to start or finish it? Okay, till the time. How much slides I'll have to cover in this module? Based on that, it will help me to where I am. Autoregressive only 28? No. Finish this. मुझे लगा कि मैं अभी भी 28 पर ही हूँ. Autoregressive 69. I'll have to cover 120. ठीक है. Let me. I won't be able to finish this in this session. Do we require one more? Which session it is? 14th, na? Is this a 14th contact session or 13th contact session? I'm missing it. Sorry. Can you please help me?
14th.
14th. So this I require, matlab I will be having 2 more. Will I be able to finish it? Because I have 2 different modules. So this is 14th contact session. I will not be taking a session on 21st of Jan. Okay, so I will have a buffer session. I will take the buffer session on 20th of May. Okay, so 21st I won't be available. So we do have only 2 days to cover. Okay, so I should not waste the time. I should quickly introduce it. 10 minutes. 10 minutes to bahut hai. Okay, so both the basic GNN and variational autoencoder based approach that we have discussed just now use simply the multi-layer perceptron to generate the edges. Now we'll introduce a more sophisticated autoregressive method that can decode the graph structure from the latent representation. Autoregressive model originates from economics and social science literature on time series data where the observation from the previous steps are used to predict the values at the current and the future time steps. Now, if you do remember, where you have encountered this word auto-regressive in the time series forecasting. Okay, but what is regressive? Basically, it can be broken into two parts. Auto means self, and the second part is the regression. Okay, regressive means regression. Regression is what? You have the data. Okay, somehow you try to fit a line, not a line, to be more specific, you try to fit a curve into the data. That curve we call it as regressive curve, such that this curve is a least square fitting method. Okay, criteria. So what is the least square fitting? Means the difference between the actual value and the predicted value has to be minimum. The square of the distance have to be minimum. Okay, so somehow you are trying to fit a curve into the data. Okay, so that was regression, or trying to fit something onto the existing data. Auto-regressive approach was introduced in your we can say the course, the module of time series forecasting, AR. Okay, in which you are trying to fit a curve based on its current value as well as its own previous value with respect to time. Okay, so the moment I'm talking about the regression, the time series forecasting, then the factor which changes is the time with the various lags. Okay, so that's why it has a wide application in the time. So time series forecasting has a wide application in the economics, and where that pointer has gone. Yeah, here it is. Okay, from the economics and social science literature on a time series data, where the observation from the previous steps are used to predict the values of a current and all the future time steps. So the shared underlying idea of this auto-regressive model is to characterize the graph generation process as a sequential decision-making process, okay, a sequential decision-making process. What to decide, I'll let you know, but that process is a decision-making, whether there should be a edge or connection between them or not. Okay, sequential means one node and that's its connectivity and so on. So sequential decision-making process, and make a new decision at each step, conditioning on all previously made decision. Okay, so your current decision, whatever you have to, or you are going to make, is based on all your previous experiences. Okay, what you have learned so far. So based on your learning, you are required to answer some questions. If you learn good, then your decision will be correct. If there's something, if it is missing something, then there'll be some problems in the prediction. So we can model this using the concept of RNN, recurrent neural network. That also work for the sequence, because here what is sequential? RNN works for the sequences. So what is the sequential? Is adding a new node and making its connectivity. So the generation of graph can also be considered as a sequence of node and edges generation. First of all, add a new node, then add a bunch of edges, then add a new node, then add the bunch of edges, and so on. So that's again some kind of sequential decision. Okay. So the recurrent neural network RNN can be used for this purpose. So it can be compared by the recurrent neural network RNN, which are far more well known. So like RNN and autoregressive models output at a time depends not only just NXT, but also X from the previous time steps as well. Okay. However, unlike RNN, the previous X's are not provided by a same hidden node. Here in this case, what is being are given as just another input to the model. Okay, so this is how is being implemented one after the another. Okay. I'll start with this. Because there's a good algorithm which we call it a teacher forcing algorithm, which is a part of RNN. Okay, I'll stop over here. Although I have covered it, but I'll give you a brief discussion. Again, a quick recap before starting up again. Okay. Why should I write it over here? I should write the stop over here. I've not even started this. Okay, fine. So we are almost finished by the time it's 3:38. We will be ending at 3:40. Fine. So we are right on time. And unfortunately, today also no break taken. So this means I'm teaching around 10 minutes, 10 to 15 minutes extra in every session. So 30 into 10, 16 into 10, around 160. So around 120 minutes, 2 hours extra. In a 32 hours, I'm taking. Okay, should I stop the recording? Anything else to be discussed on record? There's a one notification. Please go through the open book guidelines. Now something new have been banned. So please go through the guidelines for the open book exams, as there are some changes.